Okay, let's start with the basics. Memory management is all about how a computer decides where to put everything in its RAM. That's the part of your computer that holds data and instructions while it's running. It's like a really important job because RAM is limited, and we want to use it as efficiently as possible. The main goals are to make sure programs get enough space to run smoothly, give everyone a fair share, and protect them from accidentally messing up each other's stuff. We use techniques like pre-allocating memory at the beginning, static allocation, or asking for it as we need it during program execution, dynamic allocation. Okay, let's talk about why managing memory is so important for how well an application runs. Imagine RAM as a desk. It's limited in size. If an app tries to pile too much stuff on that desk, things start to slow down and get messy. When an app runs out of memory, the computer starts using your hard drive as temporary storage, which is much slower. This can cause noticeable slowdowns or even freezes. It also impacts response times. If an app is struggling with memory, it takes longer to do anything. Plus, excessive memory use can steal resources from other apps on your system. And finally, memory leaks are a big problem. They're like constantly adding more stuff to the desk without taking any away, eventually filling up the whole space. Okay, let's talk about the different kinds of memory your computer uses. The most important one is RAM, which is like a short-term workspace. It's where everything you're actively working on lives. Then there's ROM, which holds essential startup instructions and can't be easily changed. Virtual memory cleverly uses your hard drive as extra RAM when needed. And don't forget cache memory. It's a super fast buffer that helps speed things up. Finally, we have flash memory, like an SSD or USB drives, which is great for storing data permanently. Okay, let's talk about how computers remember things. Think of it like this: the stack is like a pile of plates. You put one on top, then another, and when you're done with the last one, you take it off the top. It's really fast for quickly storing and retrieving information. The heap, on the other hand, is more like a storage room. You can ask for space whenever you need it, but you have to remember to put things back when you're finished, otherwise you get what we call a memory leak. So, stack is quick and automatic, while heap gives you flexibility but requires careful management. Okay, let's talk about how the stack works for memory allocation. Think of it like a stack of plates. You always add a new plate on top and take one off the top. When a function is called, space is automatically set aside on the stack to hold things like its arguments, the values passed into it, and where the program should go when the function finishes. Importantly, variables are allocated in the order they're declared within the function, which is why it's LIFO. And just as easily as space is allocated, it's automatically freed up when a function returns, essentially taking those plates off the stack one by one. If you use too much space on the stack or create functions that call themselves endlessly, though, you can run into a Stack Overflow problem. Does that make sense? Okay, let's talk about how memory is allocated on the heap. Think of the heap as a giant pool of available space where your program can request blocks of memory whenever it needs them. It's different from the stack because you don't know exactly how much memory you'll need upfront. That's the beauty and sometimes the challenge of using the heap. The operating system's memory manager is in charge of keeping track of where all this space is, dividing it into chunks, and then giving your program blocks when you ask for them. It's not always a perfect process. Fragmentation can occur, like having little gaps between allocated pieces, but systems often use techniques to minimize that. You'll be using functions like malloc or new to get this memory, and it's really important to remember to eventually free it back up with free or delete to prevent memory leaks. Okay, let's talk about dynamic memory allocation. Think of it like renting a storage unit. You only pay for the space you actually use. Unlike static memory, where you declare how much space you need upfront, with dynamic allocation, your program asks for exactly what it needs at that moment. It's incredibly useful when dealing with data structures whose size isn't known beforehand, like linked lists or trees. Languages like C and C++ use functions like malloc and free or new and delete to manage this process, essentially requesting blocks of memory from the computer's heap. The main advantage is flexibility. you can grow or shrink your data as needed, making it a really efficient way to utilize your system's resources. Okay, let's talk about where we get our memory from when we need it during runtime. That's dynamic allocation. In C and C++, you primarily use malloc and free. Remember to always free what you allocate. Calloc is similar but initializes the memory with zeros. And then there's realloc, which lets you change the size of previously allocated blocks. Now, in Java, things are a little different because the JVM handles all the messy details for you. The new keyword creates objects in the heap, and the garbage collector takes care of reclaiming memory when it's no longer needed. Okay, let's talk about memory fragmentation. Basically, it's like having a big kitchen and constantly putting things away in small containers. Eventually you end up with lots of little piles instead of one organized space. It happens when we repeatedly allocate and release pieces of memory. There are two main types: external fragmentation, where there's enough total memory but it's broken into these unusable bits, and internal fragmentation, which is when we overallocate a block of memory reserving more than we actually need. Okay, let's talk about memory fragmentation. It's a surprisingly common interview question that really tests your understanding of how operating systems manage RAM. We have two main types: internal and external fragmentation. Internal fragmentation is when we ask for more memory than's actually physically available in a single block, like trying to fit too many pieces into a small box. That means some space gets left unused inside the allocated blocks. External fragmentation, on the other hand, happens because we have plenty of total RAM, but it's broken up into lots of little, non-contiguous chunks. Because of this, even if there's enough overall space to satisfy a request, the OS can't find one big block that works, and that can slow things down significantly. Let's summarize that in a table for quick comparison. Okay, let's talk about garbage collection. It's a really important concept in modern programming languages. Basically, the goal of garbage collection is to automatically clean up unused memory, preventing those annoying memory leaks that can slow down your application. Think of it like a cleanup crew for your program. The collector continuously monitors what objects are still being used and finds the ones that aren't. These are the garbage. It then reclaims that memory so your app has more resources to work with. There are different ways garbage collection can be done, from simple mark and sweep techniques to generational approaches, which prioritize collecting newer objects, and even reference counting, though it has some limitations. Okay, let's talk about memory leaks. Basically, it's when your program keeps holding onto memory that it doesn't need anymore. Imagine you borrow a book from a friend and never return it. Eventually, you'll run out of books. Common causes include forgetting to release memory after using it in languages like C or C++, or having event listeners attached to objects that aren't properly removed. This can slow down your program over time and even cause crashes if the system runs out of memory. Okay, let's talk about what causes those sneaky memory leaks. The biggest culprit is often just forgetting to release dynamically allocated memory. That's when you actively ask for some space with functions like malloc on you, and then forget to give it back. Another common problem is circular references, especially in languages like Python and JavaScript, where objects can point to each other endlessly, making garbage collection struggle. Global variables always hanging around are another factor, as are event handlers that keep alive unnecessarily. And sometimes, the leak isn't your fault entirely. A third-party library might be holding onto resources without releasing them. Okay, let's talk about memory leaks. They're a sneaky problem that can really mess up your software. First, we need to figure out where asterisk leaks are happening. Thankfully, there are some great tools for this. Profilers like Valgrind and Asana can pinpoint exactly where memory is being allocated but not freed. Code reviews are also super important. A fresh pair of eyes can often spot issues you might miss. Static analysis tools can even scan your code asterisk before asterisk you run it to catch potential problems. And sometimes, just carefully watching how your app behaves over time, noticing memory usage steadily increasing without any obvious reason can be a clue. Now let's talk about preventing leaks in the first place. RAI is a fantastic technique where resource management is tied to an object's lifetime. Smart pointers like unique PTR and shared PTR in C++ automate this process too. Avoid global variables holding resources. Make sure objects are destroyed when they're done with, and generally think carefully about how long your objects need to live. That really helps. Okay, let's talk about virtual memory. Think of it like this. Your computer has a limited amount of RAM, that's the space where programs actually run. But sometimes you need more than that. Virtual memory lets programs think they have access to ** more memory than is physically installed. It does this by cleverly moving pieces of code and data between RAM and a hard drive or SSD. It's like a temporary holding area. The operating system manages everything behind the scenes using something called page table, which keeps track of where each piece of information actually lives. It's all about creating an illusion of a large, continuous memory space for each program. Okay, let's talk about paging. Paging is a really clever way virtual memory manages space. Basically, both the program's address space and our physical RAM are split into equal chunks. We call these chunks pages and frames, respectively. Each has a unique number. The operating system keeps track of where each page actually lives using a table called a page table. When a program wants to access a memory location, it uses its virtual address, which is the page number, and a page table tells us exactly which frame on our RAM that data's in. Now, sometimes a page isn't loaded into RAM yet. That's a page fault. The OS then fetches it from the hard drive, bringing it into memory before continuing. Okay, let's talk about page faults. Essentially, they happen when a program tries to access something in memory that isn't currently loaded into RAM. It's like asking for a book from a library. If it's not on the shelf, you have to go find it first. The operating system then has to bring the data from storage like your hard drive into RAM, which takes time and slows things down. The more times this happens, the slower everything becomes. Okay, let's talk about segmentation faults. Essentially, they are like your program trying to access something it shouldn't, a locked door with the wrong key. It happens when a program attempts to read from or write to memory that isn't allocated to it or is already being used by another part of the program. Common causes include using memory after you've freed it, going past the end of an array, or trying to use a pointer that doesn't point anywhere valid. It's a sign that there's a problem with how your code manages its memory, and it usually means the program will crash. Okay, let's talk about how operating systems protect our programs from messing with each other's memory. It's a really important concept. Basically, they use something called virtual memory to create isolated spaces for each application. Think of it like giving each program its own little fenced-off area. Then, page tables are used to track where those programs' data lives in the computer's actual physical memory. And crucially, these page tables have permission bits read, write, and execute that tell the system exactly what a process is allowed to do with any given piece of memory. All this happens thanks to a hardware component called the Memory Management Unit, or MMU, which handles the address translations and enforces those protection rules. Okay, let's talk about memory. There are two main types. Physical memory, which is your computer's actual RAM. It's like a really fast workbench where the CPU keeps all the data it needs right now. Then there's logical memory, or virtual memory. This isn't real memory. It's how the operating system tricks programs into thinking they have more space than they actually do. It cleverly moves data between your RAM and your hard drive like a smart filing cabinet to make everything run smoothly, even if you don't have enough physical RAM available. Okay, let's talk about memory swapping. Basically, it's a clever way for computers to handle situations where they don't have enough RAM to run everything at once. Think of your computer's RAM as its short-term memory, fast and easy to access. But RAM is limited, right? Swapping lets the system use a portion of your hard drive or SSD as an extension of that RAM. When you need something that's currently stored on the disk, it gets moved back into RAM, leaving room for what's actively being used. It's slower than using RAM. Directly accessing data from a hard drive takes much longer, but it lets us run bigger programs and handle more tasks. Interviewers will often want to know about the performance impact, how the swap space is managed, and how it fits in with other memory management strategies. Okay, let's talk about memory pools. Basically, a memory pool is like having your own dedicated storage space, a predefined chunk of RAM that's set aside just for one thing. Instead of constantly asking the computer to find bits and pieces of available memory like with the general heap, you know exactly how much space you have. This speeds things up because there's less overhead when allocating and freeing memory, making your code more predictable and sometimes even a bit safer, especially if you want to limit how much memory a program can use. Okay, so let's talk about something really important for memory management: alignment. Think of it like making sure your furniture is neatly arranged in a room. You don't want things crammed together haphazardly, right? Well, computers do the same thing with data in memory. Alignment dictates that data needs to be placed at specific addresses, usually multiples of its size. Why does this matter? Because it makes accessing that data faster and smoother for the processor. If your code isn't careful about aligning integers or other data types correctly, say you're trying to read a 32-bit integer from an address that's not divisible by 4, you could end up with really slow performance or even crashing the program. It's a small detail, but it makes a big difference in how efficiently your code runs. Okay, so let's talk about pointers. They're a really important piece of the puzzle when it comes to memory management. Basically, a pointer is like an address for a location in your computer's memory. Instead of storing a value directly, a pointer holds the address where that value actually lives. It's helpful to think of it like this: you have some data, let's say a house and its address. The pointer is just the address itself. Pointers are especially useful when we need to dynamically allocate memory at runtime, meaning while our program is running, and give ourselves direct control over where data is stored in RAM. They are vital for things like creating arrays of variable sizes or managing complex data structures. Okay, let's talk about reference counting. It's a really straightforward way to manage memory. Think of it like keeping track of how many things are pointing at an object. Every object has its own little counter called the reference count. When you create a new link to that object, like assigning it to a variable, the counter goes up. And when you break that link, the counter goes down. If the counter hits 0, it means no one's using the object anymore, and we can free up its memory. It's easy to use, but be aware that it can slow things down, especially if objects are linked in circles, and it doesn't handle those circular references very well. Okay, let's talk about generational garbage collection. It's a really clever way to handle memory management. Basically, instead of treating all memory equally, it recognizes that most things we create are only around for a short time. So, the system divides the memory into different age groups, like a young area where new objects go and an old area for longer-lived ones. It collects the young area more often. Think of it like cleaning up a messy room regularly, which dramatically reduces the impact on performance compared to older methods. Let's talk about how your code holds onto objects in memory. We have 3 main types of references: strong, weak, and soft. Strong references are the usual suspects. They mean that an object is actively being used and won't be cleaned up until it's no longer needed. Think of a variable assigned to an object. That's usually a strong reference. Weak references let go of ownership, allowing the garbage collector to reclaim memory even if there are still weak references pointing to something. This can be handy for things like caching. You want to keep data around, but you don't want it to block the program from running out of memory. Finally, soft references are a bit more flexible. The garbage collector will only get around to cleaning them up when memory is really tight. It's like saying I'd like asterisk to keep this object around, but if I need the space, I'll let it go. Okay, so when we're talking about memory management in C++, smart pointers are a really important tool. Think of them as regular pointers, but they've got built-in safety nets to stop us from making mistakes like memory leaks or dangling pointers where you're trying to use memory that's already been freed. There are a few different types. Unique PTR means only one pointer can own an object, which is great for preventing copies and accidental access. Then there is shared PTR, which allows multiple pointers to share ownership of the same object, and it automatically handles when no one's using that object anymore. Finally, you have weak PTR, which just observes a shared pointer without actually taking ownership. Okay, so let's talk about optimizing memory, a really important area for any software developer. The first step is always to figure out where your app is using too much memory. We do this by using profiling tools that can help us spot leaks and see exactly what's consuming the most space. Then we can think about strategies like object pooling, which means reusing objects instead of constantly making new ones. Selecting the right data structures, like using a bitset if you only need to store flags, also makes a big difference. And don't forget smart pointers and RAI. These help us manage memory automatically and prevent those pesky leaks. Okay, let's dive into how you'd investigate memory issues. A really important skill is knowing what tools are available to help you track down where your application is using up all that precious RAM. Some common choices include Valgrind on Linux, a fantastic debugger for spotting leaks and errors. On macOS, Instruments within Xcode gives you a ton of detailed information about memory and performance. For heap analysis specifically, HeapTrack can be super helpful. And if you're working with NET applications, Visual Studio's built-in memory profiler is a good option. Finally, for web development, Chrome DevTools has a really effective memory profiler. The best tool depends on your platform and project, so knowing what options exist is key. Okay, let's talk about out-of-memory errors. They are a common pain point in software development. Basically, an OOM error happens when your program tries to use more memory than your computer has available. This can lead to some serious problems. It often stems from things like memory leaks, where you keep allocating but not releasing memory, or trying to load massive datasets that exceed the RAM capacity. To tackle this, you'll want to start by profiling and monitoring your application to find exactly where the memory is being used excessively. Then, a thorough code review can help spot potential leaks or inefficient data structures. Don't forget about optimizing your algorithms and even considering increasing the available memory, but always do that cautiously. Okay, so let's talk about how the JVM keeps track of everything and make sure we don't run out of memory. The biggest area is called the heap. That's where all your objects live. It's actually divided into a few parts: the young generation, where new things are born; the old generation for objects that have proven they stick around; and then the permgen or metaspace, which holds essential information about our classes. Outside of that, you've got the stack, method area, and direct memory, all important but smaller. The really cool part is garbage collection. The JVM automatically cleans up unused memory, so we don't have to worry about manually managing it. There are different ways the JVM does this, each with its own strengths and weaknesses. Okay, let's talk about how the JVM manages memory. It's divided into two main areas: the young generation and the old generation. Think of it like this: the young generation is where all new objects are born, and they tend to live a short life. They get garbage collected pretty regularly in what we call minor GCS. The old generation is where longer-lived objects reside, the ones that have made it through several rounds of minor collections. These are the things you really want to keep around. The JVM uses this generational approach because it's much more efficient than collecting everything all at once, especially when dealing with a lot of new objects. Okay, so let's talk about memory allocators. They are absolutely crucial for how programs actually run. Basically, a memory allocator is like the traffic controller for your computer's RAM. It's in charge of giving pieces of memory to your program when it needs them, and then taking those pieces back when the program is finished with them. It prevents things from getting messed up by making sure that memory isn't used twice or lost entirely. A key part of its job is dealing with something called fragmentation, where you end up with lots of little bits of unused space scattered around, which can be a real headache. Okay, so let's talk about heap compaction. Imagine your computer's memory is like a messy room with lots of little boxes, objects scattered everywhere. Over time, as you create and destroy things, those boxes get moved around, and the room gets fragmented. It's harder to find big enough spaces to put new things. Heap compaction is essentially cleaning up that mess. It moves all the objects together, making bigger blocks of available memory so we can allocate more efficiently and avoid wasting space. Okay, let's talk about stack overflows. Basically, it's a really common problem in programming, especially when dealing with recursion. Imagine the call stack as a pile of plates. Each time a function calls itself, you add another plate to the top. If you keep adding plates without taking any away, eventually the pile gets too big and collapses. This happens because the program is trying to use more memory on the stack than it has available. It's most often caused by functions that call themselves repeatedly without a proper stopping point. We call this uncontrolled recursion. Sometimes the operating system just doesn't give your program enough space on the stack in the first place. Okay, let's talk about memory maps. Basically, it's a mental picture of how your computer's RAM is laid out. It's like a detailed street plan for all the programs running on your machine. You've got code segments, that's where your program's instructions live. Then there are data segments holding variables and constants. The stack segment, that's like a temporary workspace for function calls, and the heap is where you get memory dynamically as needed during runtime. Knowing this layout can be super helpful when debugging or trying to improve performance. Okay, let's talk about how different processes can actually use the same chunks of memory. A really common technique used by operating systems is something called shared memory. Basically, we designate a specific area in RAM or computer's main memory that multiple programs can access at the same time. It's like having a communal whiteboard that everyone can write on. There are different ways to set this up. POSIX shared memory is a standardized approach, and there's also an older system called systemd shared memory. Another really useful method is memory mapping. It's like giving each process a direct route into a file or device so they don't need to copy the data around. Okay, let's talk about copy on write. It's a really neat trick in how computers manage memory. Think of it like this. When a program wants to change something that's already in memory, instead of making the actual changes directly, the system creates a brand new copy of that memory area. So, if multiple programs are using the same piece of data, they each get their own independent copy. This means modifications only happen on those individual copies, keeping everything nice and organized and avoiding unnecessary duplication. It's really a smart way to make memory use more efficient. Okay, let's talk about memory map files. Basically, these are a clever way to work with really big files. Instead of loading the whole thing into your computer's RAM, which could cause problems if it's too large, you create a virtual address space that mirrors the file on disk. It's like giving your program a direct window into the file, and the operating system takes care of reading from or writing to the actual disk as needed. This means you can access those huge files much faster and use less memory overall. Pretty handy, right? Let's talk about cache memory. It's like a super fast scratchpad for your computer, helping it retrieve frequently used data much quicker. Basically, the CPU checks the cache first before going all the way to RAM. That's why things feel faster. Cache works because programs tend to reuse data and instructions nearby in time and space. There are different levels of cache, with the fastest closest to the CPU. This helps drastically reduce wait times and makes your computer run smoother. Let's talk about double buffering. It's a clever trick to make graphics look smoother and avoid annoying screen flickering. Think of it like this. We have two screens. One is showing what you see on your monitor, the front buffer, and the other is where all the new drawing happens, the back buffer. As soon as the current image is finished being drawn on the back buffer, we instantly swap those two screens. Boom. The old image disappears and the fresh one appears. It's a really efficient way to ensure that you always see a complete, stable picture without any gaps or flashes. Let's talk about tuning your garbage collector. It's all about making sure you're not spending too much time cleaning up memory and that your application stays responsive under pressure. First, start by profiling, see where the memory issues are coming from. Then pick a collector that suits your app. Some are better for low latency systems, while others focus on speed. It's also important to set the right heap size, considering both how much memory you need and how efficiently it's being used. And finally, if you're using a collector like Gone, experiment with things like pause time settings to find the sweet spot between performance and responsiveness. Remember, small changes based on what you discover through profiling will always be more effective than just randomly tweaking settings. Okay, let's talk about tackling big objects when memory is tight. The simplest thing, just allocating them directly, can quickly lead to problems. My go-to strategy is usually object pooling. Essentially, we reuse existing objects instead of constantly creating new ones. If we know that something will be created and destroyed repeatedly, this saves a lot of overhead. Another option is pre-allocation, setting aside a chunk of memory upfront for frequently used objects. For huge files, memory mapping is fantastic because it lets us work with the data directly from disk without moving it into RAM. And sometimes we can break things down into smaller chunks and process them individually, and then combine the results. Finally, if we have control over how long an object lives, using RAI in languages like C++ can help ensure that memory is released properly when it's no longer needed. Okay, let's talk about object pooling. Basically, it's a clever trick to avoid constantly creating and destroying objects, which can really slow things down. Imagine you need to connect to a database over and over again. Every time you do, it takes some time to set up that connection. Object pooling keeps a bunch of connections ready to go, so when you need one, you just grab an existing one from the pool instead of starting fresh. It's really useful for things like database connections or network sockets. Anything where creating and destroying objects is a performance bottleneck. You'll also find it helpful if you're dealing with complex objects that take a long time to build up. Just remember, because multiple threads might be accessing the pool at the same time, you need to make sure your code handles those situations safely, often through locking or other synchronization techniques. Okay, let's talk about data locality, a really important concept in memory management. Basically, it's all about how close your program's data is to where the computer can access it quickly, which is RAM. There are two key types: temporal locality, meaning if you use something once, you'll likely need it again soon, and spatial locality, which says that if you access one piece of data, nearby bits are probably going to be needed too. The reason this matters so much is because accessing data in RAM is fast, like, dramatically faster than reading from a hard drive or SSD. When your program has to go hunting for data elsewhere, it slows everything down significantly, impacting both performance and power usage. Okay, let's talk about how memory paging affects performance. Think of it like this: your computer's RAM is a really fast disk, but it has limited space. When you need more room, you can move some things to a slower shelf. That's essentially what paging does. It moves inactive parts of programs to the hard drive or SSD. But here's the catch: accessing those things on the shelf is much slower than grabbing them from your desk. This constant swapping creates page faults, which are like little delays every time a program needs data that isn't already in memory. If this happens too often, it can lead to a frustrating situation where the computer spends all its time switching things around instead of actually doing anything useful. That's called thrashing. Operating systems try to be smart about this by keeping the most used pages close at hand, but it always comes with a performance trade-off. Okay, let's talk about virtual address space. It's a really important idea in understanding how computers work. Imagine your program is asking for an address like 1000, that's virtual address. But the actual memory location where that data lies could be anywhere in physical RAM. The operating system and something called the Memory Management Unit, or MMU, handle this translation in real time. It's all about creating an illusion of a huge, contiguous block of memory for your program, even if the computer's actual RAM is smaller and potentially scattered around. This allows multiple programs to run simultaneously without stepping on each other's toes. Okay, let's talk about how operating systems fight against memory corruption, a huge deal in security. Basically, they use a combination of hardware and software tricks. MPU are like walls around code, stopping it from messing with other parts of memory. Virtual memory is super important too. It creates an illusion that each program has its own separate space. An ASR? That's all about shuffling things around randomly to confuse attackers. Then there's stack canaries, a safeguard specifically designed for buffer overflows. Finally, DEP, or NX-bit as it's sometimes called, prevents code from being injected into areas where data should reside. These techniques work together to make memory corruption attacks far more difficult. Thank you for watching.